Machine learning, or ML, is a branch of artificial intelligence focused on building systems that learn from data. It enables computers to make decisions with minimal human intervention. As we generate more data every day, ML helps to make sense of this vast information. It is used in various fields such as healthcare, finance, and technology. Understanding ML is essential for modern-day problem-solving. It equips professionals with tools to automate processes and make predictions. The importance of ML is evident in its ability to personalize user experiences. For instance, recommendation systems in Netflix or Amazon rely heavily on ML algorithms. In the coming sections, we will break down key concepts of ML. This will include types of learning, data handling, and model evaluation. We will also discuss advanced topics and next steps for further learning. Machine learning is categorized into three main types: supervised, unsupervised, and reinforcement learning. Each type has its unique characteristics and use cases. Understanding these distinctions is crucial for applying the right algorithm to the right problem. Supervised learning involves training a model on a labeled dataset. This means that each input comes with a corresponding output. The model learns to map inputs to outputs by finding patterns. It is commonly used for tasks like classification and regression. Examples include spam detection and house price prediction. Unsupervised learning, on the other hand, deals with unlabeled data. The model tries to uncover hidden patterns or intrinsic structures in the data. Clustering and association are typical tasks in unsupervised learning. This type is useful for customer segmentation and market basket analysis. Reinforcement learning involves an agent that learns by interacting with its environment. It makes decisions to maximize cumulative rewards. This type is often used in gaming, robotics, and autonomous driving. The agent learns from trial and error, improving over time. Data is the backbone of any ML system. The quality and quantity of data directly impact the model's performance. Raw data often contains noise, missing values, or irrelevant features. Hence, data pre-processing is a critical step. It involves cleaning, transforming, and organizing data. Data pre-processing starts with data cleaning. This step removes or corrects errors and inconsistencies. Techniques like imputation and normalization are commonly used. Finally, data is split into training and testing sets. The training set builds the model, while the testing set evaluates it. Section 4. Supervised learning with examples. In supervised learning, the model is trained on a labeled dataset. Each input data point has a corresponding output label. The goal is to learn a mapping from inputs to outputs. There are two main types: classification and regression. Classification predicts categorical labels. For example, classifying emails as spam or not spam. Common algorithms include logistic regression and decision trees. Regression predicts continuous values, like house prices. Linear regression is popular for this task. Supervised learning is widely used in various applications. Section 5. Unsupervised learning techniques. K-means and dimensionality reduction. Unsupervised learning deals with unlabeled data. The model tries to find patterns or structures in the data. Clustering and dimensionality reduction are two main techniques in unsupervised learning. These methods help in understanding complex datasets. K-means is a popular clustering algorithm. It partitions the data into K-clusters based on similarity. Each data point belongs to the cluster with the nearest mean. This technique is useful for customer segmentation and image compression. It helps in grouping similar items together. Dimensionality reduction techniques like principal component analysis, or PCA, reduce the number of features. PCA transforms the data into a lower dimensional space while preserving most of the variance. This is useful for visualization and speeding up computations. It helps in dealing with high-dimensional data. Both techniques have their applications in real-world problems. Clustering helps in organizing large datasets, making them easier to analyze. Dimensionality reduction simplifies complex data, making it more manageable. These techniques are essential for exploratory data analysis. Section 6. Neural networks and deep learning. Neural networks are the backbone of deep learning. Inspired by the human brain, they consist of layers of interconnected nodes or neurons. Each neuron performs a simple computation, solving complex problems together. Deep learning extends neural networks by adding more layers, called deep architectures. CNNs are used for image recognition, while RNNs are suitable for text and speech. Deep learning has revolutionized many fields. In computer vision, it enables advanced image and video analysis. In natural language processing, it powers machine translation and sentiment analysis. Training deep learning models requires large data sets and significant computational power. Understanding the basics of neural networks is a stepping stone to mastering deep learning.